So this is number theory, lecture 16. And the first thing I want to do is to review and expand what we know about the Euler phi function. And phi is a Greek letter, which looks like this. And for any number positive integer m, phi of m is the number of integers a from 0 up to m minus 1, such that the greatest common divisor of a and m is equal to 1. And we computed phi of m for various values of m. And we also could prove certain things about the value of phi for special numbers. For example, if p is a prime, then phi of p is the number of integers a from 0, 1 up to p minus 1, such that a and p is equal to 1. And 0 and p have greatest common divisor p, but the integers in this set, which are relatively prime to p, are all the non-zero numbers, the numbers from 1 to p minus 1. So phi of p is equal to p minus 1 for every prime p. And in general, for any positive integer k, if we want to look at phi of p to the k, what can we say? So an integer a is not relatively prime to p to the k, so this greatest common divisor is greater than 1. Well, the only divisors of a prime power are prime, the same prime powers, but lower powers maybe. So a and p to the k are a greatest common divisor greater than 1 if and only if p divides a. So if you look at the numbers from 0 up to p to the k minus 1, we want to exclude all the multiples of p. So what are they? 0 times p, 1 times p, 2 times p. What's the largest multiple of p you can get? You can get, let's see, p to the k minus 1 times p, because this is p to the k minus p. That's less than p to the k. The next larger multiple of p is p to the k minus 1 times p, which is p to the k, which is bigger than p to the k minus 1. So it's not in this set. So how many multiples of p are there between 0 and p to the k minus 1? There's p to the k minus 1 plus the 0 plus 1. There's p to the k minus 1. So we exclude p to the k minus 1 numbers. So of the p to the k numbers between 0 and p to the k minus 1, we throw out p to the k minus 1, and everything that's left is relatively prime to p to the k. So p to the k is equal to this, which if you want, you could write as, let's see, p to the k minus 1 is p to the k divided by p. If I factor out a p to the k, I get 1 minus 1 over p times p to the k. So these are all equivalent formulas for what phi of p to the k is. So that's a basic formula you have to know. And for example, phi to the 9 is 3 squared. So when p is equal to 3, that's 1 minus a third times p squared. So that's 2/3 times 9, that's 6. So phi of 9 is equal to 6. Or one of the questions on the exam, what is phi of 25? That's phi of 5 squared. That's 1 minus a fifth times 5 squared. That's 4/5 times 25. 5 into 25 is 5. And 4 times 5 is 20. Okay. Any questions about this? So I want to prove some more properties of the Euler phi function. And the first is that it is, in a certain sense, multiplicative. So what we call an arithmetic function is a function f whose domain is the positive integers. It can be real or complex value. So this is the positive integers. So for example, phi of m is an arithmetic function because it's defined for all positive integers m, for all m and n. And we say that an arithmetic function is multiplicative if f of mn is f of m times f of n. Now, if this were all there were to the definition, and it's not, this would be something like a homomorphism in algebra. So if f of mn were equal to f of m times f of n for all positive integers m and n, that'd be very nice. But a multiplicative function has to satisfy this condition, not for all pairs, but only for some pairs, whenever m and n are relatively prime. And we're going to prove that the Euler phi function, phi of m, is multiplicative. Let's look at an example. Phi of 3 is 2, because 3 is a prime. And phi of 5 is 4, because 4 is a prime. What is phi of 15? So if you look at the numbers, from 0 to 14, and you cross out all the numbers that are not relatively prime to 15. So that means all the numbers divisible by 5 and all the numbers divisible by 3. How many numbers are left? 1, 2, 3, 4, 5, 6, 7, 8. So phi of 15 is equal to 8. But 15 is 3 times 5, and the greatest common divisor of 3 and 5 is 1. And if you take phi of 3 times phi of 5, phi of 3 is 2, phi of 5 is 4, that's 8. So phi of 15, so in this example, we see phi of 15 is phi of 3 times 5 is in fact phi of 3 times phi of 5. So this is an example of what it means to say that the Euler phi function is multiplicative. Okay. So this is an important concept in number theory. Number theory is about, to a great extent, arithmetic functions, and phi of m is an arithmetic function, which we know is defined for all positive integers m. Okay. And how do we prove phi of m is multiplicative? This takes a little bit of work. What is one consequence of that? So suppose we take a positive integer m, and by the fundamental theorem of arithmetic, we can write m as a product of primes, p1 to the v1, p2 to the v2, up to pk to the v sub k. So where p1, p2, up to p sub k are distinct primes, and v1, v2, up to v sub k are positive integers. So this is writing m as a product of prime powers. And multiplicativity implies semi-legible. Let me just make it clear. It's all clear in the book, of course. Multiplicativity implies that if m1, m2 up to m sub k are pairwise relatively prime, that means that mi and mj have greatest common divisor 1 for all I and j, then phi of this product is the product of the phis. So if an arithmetic function is multiplicative, which means this statement is true for k equal 2, then it's easy to show by induction that if m1 up to mk are pairwise relatively prime, that this multiplicative property holds for any number of factors. So in particular, if m is p1 to the v1, p2 to the v2, up to pk to the v sub k, these are distinct prime powers. So pi to the vi and pk to the vi are relatively prime because their powers are different primes, pj to the vj. These are pairwise relatively prime integers for I different numbers between 1 and k. And so phi of m is phi of p1 to the v1, p2 to the v2, up to pk to the vk, then it's the product, phi of p1 to the v1, phi of p2 to the v2, up to phi of pk, or sorry, f, if f is any such multiplicative function. These are all, this is a statement about any multiplicative function. F of m, f of p1. So f of m is f of p1 to the v1, f of p2 to the v2, up to f of pk to the vk. So whenever f is a multiplicative function, f of m, when you factor m into a product of primes, which you know you can do by the fundamental theorem of arithmetic, you get this result. And if you apply this to the Euler-Phi function, once we prove that the Euler-Phi function is multiplicative, it says that phi of m is phi of p1 to the v1, phi of p2 to the v2, up to phi of pk to the vk. But we just proved what each of these is. This is 1 minus 1 over P1 to the V1, 1 minus 1 over P2 to the V2, up to 1 minus 1 over pk to the vk. I multiply all these primes together, I just get m. And so what I get is 1 minus 1 over P1, 1 minus 1 over P2, up to 1 minus 1 over pk times m, where these are the distinct primes that divide m. So we have the following theorem, which says that the Euler function phi of m being multiplicative implies that for any m, phi of m is the product over all the distinct primes that divide m, 1 minus 1 over p times m. So this is a very, very, very useful theorem, so long as you can factor m. So for example, what is phi of 600? What is phi of 600? So you have to write 600 as a product of primes. So 600, let's see, that's 6 times 100. 6 is 2 times 3. 100 is 4 times 25. That's 2 times 3. 4 is 2 squared. And 25 is 5 squared. So if you write the prime factorization of 600, this is 2 cubed times 3 times 5 squared. The primes dividing 600 are 2, 3, and 5. So phi of 600 is the product of the primes dividing 600, 1 minus 1 over p, times 600. What are the primes dividing 600? 2, 3, and 5. So we get 1 minus a half, 1 minus a third, 1 minus a fifth, times 600. That's equal to a half times 2 thirds times 4 fifths times 600. Let's see, what is that? This is, the 2's cancel. That's 4 over 15 times 600. 15 into 60 goes 4, so 15 into 600 goes 40. So phi of 600 is 160. So once you know phi of m, the Euler phi function, is multiplicative, you have this beautiful formula. And so what's left, which is the hard part, is must prove phi of m is multiplicative. And the tool for proving this, I should say that this result in the text, this is theorem 2.7. And the tool for proving theorem 2.7 is what is in the text, theorem 2.6. And it says the following. Let m and n be relatively prime positive integers where every integer c, there exist unique integers a and b such that a is between 0 and n minus 1, b is between 0 and m minus 1, and c is congruent to ma plus nb modulo m times n. Okay. Moreover, C is relatively prime to Mn, n times n, if and only if, in this representation, A is relatively prime to n, and B is relatively prime to m. So pause for a minute to look at this, because there's a lot of number theory built into this theorem. This is both an existence and a uniqueness theorem. So if you take any of the least non-negative residues mod n, those are the A's, and any of the least non-negative residues mod m, those are the B's, then every number is congruent to ma plus nb mod mn, and uniquely. So if you take different A's and B's, you get different C's. And that actually is the first thing we're going to prove. So proof. Suppose we have numbers A1 and B1, and we look at MA1 plus NB1, and we have numbers A2 and B2, and we look at MA2 plus B plus NB2, and these are congruent modulo Mn. I want to prove, we'll prove that A1 is congruent to A2 mod n, and B1 is congruent to B2 mod n. So how do we prove this? We have this relationship. This says that this number minus this number is divisible by mn. So if it's divisible by m times n, it's certainly divisible by n. Because this difference is divisible by m times n, so it's divisible by n. But these are both 0 mod n. So MA1 is congruent to MA2 mod n, which means n divides this difference, MA1 minus MA2, that is m divides m times A1 minus A2. But m and n are relatively prime. So we apply Euclid's lemma. If n divides a product of two numbers and it's relatively prime to one, it divides the other. So n divides m times A1 minus A2. N is relatively prime to m, so n divides A1 minus A2, which means A1 is congruent to A2, mod n. And if we apply the same argument, looking at this congruence modulo m, these cancel. NB1 becomes congruent to NB2 mod m. M and n are relatively prime, so B1 is congruent to B2 mod m. So what we proved is that if MA1 plus NB1 is congruent to MA2 plus NB2 modulo MN, then A1 is congruent to A2 mod N, and B1 is congruent to B2 mod M. But if, in addition, A1 and A2 are between 0 and n minus 1, between 0 and n minus 1, the difference between two numbers is only divisible by n if the numbers are the same. A1 equals A2. And if B1 and B2 are between 0 and m minus 1, then the only way two such numbers are congruent is if they're the same. So the set of numbers A1 M let's put it the other way. The set of numbers MA1 plus NMA plus NB mod M are distinct for A's and B's satisfying these congruences. And how many such numbers are there? You have n choices of A, you have m choices of B, so you have mn choices of the pair AB, and these are distinct mod mn, but there only are mn congruence classes mod m. So these represent every congruence class. So therefore, for all C, there exists A and B unique, where A is between 0 and n minus 1, B is between 0 and m minus 1, and MA plus NB is congruent to C mod MN. So that is a proof of the first part of the theorem, and there's a lot in the proof to understand. There are many, many, many steps to the proof. Each requires you to be able to justify the step. And how do we prove the statement about relatively prime integers? So the second part of the proof says the following: if C is relatively prime to Mn, then we know that there exist unique A and B in this range with C congruent to MA plus NB mod Mn. And so this is the new part. If C is relatively prime to M and N, then A is relatively prime to N and B is relatively prime to M. Right? So I have to prove this additional statement. So let's look. What is the greatest common divisor of C and M? So it's 1, of course. So CM, the greatest common divisor of C and M, If C is congruent to MA plus NB, let me do it the way I did it in the text. So if C is congruent to MA plus NB mod MN, the greatest common divisor of C and M is going to be the greatest common divisor of MA plus NB with M. Now, if a number D, if this greatest common divisor is D, if D divides M and it divides this, if D divides M, it divides MA, so D is going to divide NB. So this will be the greatest common divisor of NB and M. And if M and N are relatively prime, that was our hypothesis. M and N are relatively prime. If something divides M and NB, it better divide B, because the only number that divides both M and N is 1. So this is B and M. And similarly, the greatest common divisor of C and N is MA plus NB, greatest common divisor with N. This is the greatest common divisor of MA and N. Greatest common divisor of M and N is 1, so the greatest common divisor of MA and N is A and N. So we can say that C is relatively prime to Mn, if and only if C is relatively prime to M and C is relatively prime to N. Because if this greatest common divisor were bigger than 1, there would be a prime that divides C and Mn. If a prime divides Mn, it divides either M or N. So one of these would be bigger than 1. So if this greatest common divisor is bigger than 1, then this is not true. On the other hand, if the greatest common divisor is 1, then C and M and C and N are both relatively prime. And by this is the same as saying that BM and AN are relatively prime. So that's the proof of this theorem. And it's a hard theorem. You need to spend a lot of time trying to understand it. But this theorem implies multiplicativity. So I said what theorem 2.6 is. That's what I just wrote. And I said theorem 2.7 says that the Euler-Phi function is multiplicative. And I claim that theorem 2.6 implies theorem 2.7. So how do we prove that? So phi of Mn is the number of C that are relatively prime to M and N. But every C that's relatively prime, every such C can be written as A N M A plus NB, where A is between 0 and N minus 1, B is between 0 and M minus 1, and AN equals BM equals 1. The number of such A's, the number of choices of A is phi of M. The number of choices of B is phi of N. Sorry, the number of choices of A is phi of N. The number of choices of B is phi of M. So phi of Mn equals phi of M times phi of N. So that, marvelously enough, completes the proof of our theorem. And again, let me just restate the two main facts. The first is the multiplicativity of the Euler-Phi function. And the second is the formula that says phi of M is equal to the product over all the distinct primes dividing M, 1 minus 1 over P, that number times M. Let's do another example. What's phi of 1,001?
Is that the formula?
Sorry?
Is that the formula?
That's the formula for phi of m.
Okay.
So what is phi of 1,001? Well, you have to know how to factor 1,001. And that's one of my favorite numbers. We've seen this before. 1,001, I believe, actually factors into 7 times 11 times 13. Let me just check that that's correct. Yeah. So 1,001 is 7 times 11 times 13. So phi of 1,001, what are the primes that divide 1,001? Well, 7, 11, and 13. So we get 1 minus 1 over 7, 1 minus 1 over 11, 1 minus 1 over 13 times 1,001. So that's equal to 6 over 7 times 10 over 11 times 12 over 13 times 1,001, which is 6 times 10 times 12 over 7 times 11 times 13. And we already saw 1,001 is 7 times 11 times 13. So this denominator cancels. We get 6 times 10 times 12, which is 720. So the number of integers from 0 to 1,000 that are relatively prime to 1,001, that number is exactly 720. Here's a problem for you to do right now, just for fun. Compute phi of 140. What is that going to be equal to? I'll pause for a moment to give you a chance to try to calculate that. The first thing you have to do is factor 140. Let's see, that's 10 times 14. 10 is 2 times 5, and 14 is 2 times 7. So this is 2 squared times 5 times 7. So the primes that divide 140 are 2, 5, and 7. So you get 1 minus a half, 1 minus a fifth, 1 minus a seventh times 140. That's 1 half times 4 fifths times 6 sevenths times 140. Let's see, 2 times 5 times 7. This is 70. This is 24 over 70 times 140. 70 into 140 goes twice, and 24 times 2 is 48. So phi of 140 is 48. Any questions about that? So there's one last theorem about the Euler phi function, which has to do with summing the values of the Euler phi function over different divisors of the number. So let's take, for example, m equal to 6. What are the divisors of 6, the positive divisors of 6? 1, 2, 3, and 6. Phi of 1 is 1. Phi of 2 is 1. Phi of 3 is 2. Phi of 6 is also 2. So if I take phi of 1 plus phi of 2 plus phi of 3 plus phi of 6, that's 1 plus 1 plus 2 plus 2, that's 6. So I can write this as, this is the sum of phi of d over all the positive divisors of 6. And if I sum phi of d over the positive divisors of 6, I get 6. Huh. Let's take 8. What is the sum of phi of d over the positive divisors of 8? So the numbers that divide 8, the positive integers, are 1, 2, 4, and 8. Phi of 1 is 1. Phi of 2 is 1. See, the numbers relatively prime to a power of 2 are just the odd numbers. So the odd numbers up to 4, there are 2 of them. And the odd numbers up to 8, there are 4 of them. 1 plus 1 is 2, plus 2 is 4. You get 8 back. So if I sum over the divisors of 8, phi of d, I get 8. Huh. That's cute. Let's do another example. Suppose I take, let's make it more interesting. Suppose I take the sum over all the divisors of 30. 30 has a lot of divisors. What are the divisors of 30? 1, 2, 3, 5, 6, 12, 15, and 30. There are 8 of them. So I want to compute phi of 1 plus phi of 2 plus phi of 3 plus phi of 5 plus phi of 6 plus phi of 12 plus phi of 15 plus phi of 30. So some of these are easy. Phi of 1 is 1. 2 is a prime, so phi of 2 is 2 minus 1. 3 is a prime, so phi of 3 is 3 minus 1. 5 is a prime, so phi of 5 is 5 minus 1. That's 4. For 6, what are the numbers relatively prime to 6? Between 0 and 6, or between 0 and 5, or 1 and 6? Just 1 and 5, that's just 2. What is phi of 12? Let me just do this calculation. Phi of 12 is the divisors, the prime divisors of 12 are 2 and 3. So that's a half times 2/3 times 12. That's 4. So phi of 12 is 4. What is phi of 15? 15 is 3 times 5. The prime divisors of 15 are 3 and 5. So I get 1 minus 1/3. 1 minus 1/5 times 15. That's 2/3 times 4/5 times 15. That's 8. And what is phi of 30? 30 is 2 times 3 times 5. So the prime divisors of 2 are 2, 3, and 5. I get 1 minus 1/2, 1 minus 1/3, 1 minus 1/5 times 30. That's 1/2 times 2/3 times 4/5 times 30. That's also 8. So if I sum the Euler phi function, phi of d over all divisors d of 30, I get this. This is 2, 4, 8, 10, 14, 22, 30. So in all 3 cases, when I summed over the divisors of number, here I summed over divisors of 6, I got 6. Here I summed over the divisors of 8, I got 8. Here I summed over the divisors of 30, I got 30. And these are instances of the following theorem, which says this is always true. For any positive integer m, if I take the sum over all the divisors of m, phi of d, that's always equal to m. So this is theorem 2.8. It's a really interesting and beautiful theorem. So let's prove this. Let's first look at a special case where m is just the power of a prime. M is equal to p to the L. At least one. So the divisors of p to the L are just the powers of p. 1p, p squared, p cubed, up to p to the L. So if I sum over all divisors of p to the L, phi of d, this is a sum of phi of p to the k, where k goes from 0 to L, right? 1 is p to the 0, p to the first power, up to p to the L. This is the sum from 0 to L. Well, I actually computed what phi of p to the k is. Phi of p to the k, one expression was p to the k minus p to the k minus 1. Because you have, if you're looking at p to the k, you have p to the k minus 1, multiples of p up to p to the k, take those away, everything left is not divisible by p. Sorry, except when k equals 1. And phi of 1 is 1 plus 1. So what is this? This is 1, that's the 1, plus when k is 1, I get p minus 1. When k is 2, I get p squared minus p. When k is 3, I get p cubed minus p squared, all the way up to when k is L, p to the L minus p to the L minus 1. And this is what's called a telescoping sum. Everything cancels. The 1 cancels the minus 1. The p cancels the minus p. P squared cancels minus. Everything cancels up till you get to this last term, which is p to the L. So what we just proved that this formula is certainly true when m is a power of a prime. But what about the general case? So the general case is m is some product of prime powers, say p1 to the r1, p2 to the r2, up to pk to the r sub k. And sorry, let me just follow the notation in my notes or in the book. We call these powers exponents t. So this is p1 to the t1, p2 to the t2, pk to this p sub k. And if d divides m, then d has to be a product of powers of these same primes, p1 to the r1, p2 to the r2, pk to the r sub k, where for every one of these primes, the exponent ri is between 0 and t sub I. Right? So this is m, and this is a divisor of m. It's a product of the same primes where the exponents are no greater than the exponents occurring in the original m. And because phi is multiplicative, phi of d is phi of P1 to the R1 up to PK to the RK. That's the product phi of P1 to the R1 up to phi of PK to the R sub K. So if you're taking the sum over all divisors of M, phi of D, that's a sum of numbers of this form, phi of P1 to the R1, phi of P2 to the R2, up to phi of P sub K to the R sub K, where this is a sort of a multiple sum. R1 goes from 0 to T1, up to RK goes from 0 up to T sub K. And you can actually disentangle this sum and write this as a product. I goes from 1 to K times the sum of phi of Pi to the Ri. I goes from Ri goes from 0 to T sub I. But this is a sum over all the divisors. So this is the product. I goes from 1 up to K. This is a sum over all the divisors of Pi to the T sub I, phi of D. And we just proved this result for prime powers. So this is a product. I goes from 1 up to K, P sub I to the T sub I, which is M. So that's the result. And everything we did today is, from the point of view of number theory, complicated. Not impossibly complicated, but it is complicated, and it takes some time to think about all of this and work it out and try to understand it. And almost everyone will have difficulty studying this stuff to understand everything. And that's why we have Zoom office hours every day this week, Monday to Thursday at 7 o'clock. Okay. So that is a great deal more about the Euler phi function. And there's one more result I want to prove today, which is in section 2.4. And CRT stands for Chinese remainder theorem. And the Chinese remainder theorem is a theorem about, for example, instead of solving two equations in two unknowns, we're solving two congruences with two different moduli. So the first form of the Chinese remainder theorem, this is theorem 2.9, says the following. We have positive integers m and n, which are relatively prime. And we also have integers, positive or negative a and b. And the question is to solve, if we can, find a number which is simultaneously congruent to a mod m and congruent to b mod n. So given two such congruences, see if you can solve them. So for example, suppose I take m equal to 6 and n equal to 10. And I take a equal to 3 and b equal to 7. So I want to try to solve. So what are the congruences in this case? I want to try and solve x congruent to 3 mod 6 and x congruent to 7 mod 10. I want to find one integer that solves both of these congruences. Let's see. Let's try to do that. So if x is congruent to 3 mod 6, then x has to be equal to 3 plus 6y for some y. But then x, which is 3 plus 6y, then has to be congruent to 7 mod 10, which is the same as saying 6y is congruent to 4 mod 10. And if I take y equal to minus 1, I get a solution because minus 6 minus 4 is minus 10. So one solution is if I take y equal to minus 1, and if y is equal to minus 1, x is 3 minus 6 or minus 3. So one solution of this pair of congruences is x equal to minus 3. Minus 3 minus 3 is minus 6 divisible by 6. Minus 3 minus 7 is minus 10 divisible by 7. Another solution would be x equal to 27. Of course, 27 is congruent to 3 mod 6. 6 divides 24, which is 27 minus 3. And 27 is congruent to 7 mod 10, because 10 divides 20, which is 27 minus 7. So this pair of congruences has a lot of solutions, mod 10. So this is an example of solving two congruences. Let's look at another example. Suppose I wanted to solve x congruent to 2 mod 6 and x congruent to 7 mod 10. So again, if there's a solution, if x is 2 mod 6, then x is equal to 2 plus 6y. So if I plug that into the second congruence, that means 2 plus 6y has to be congruent to 7 mod 10, which means 6y is congruent to 5 mod 10. And this has a solution. Remember, ax congruent to b mod m is solvable if and only if b is congruent to 0 modulo the greatest common divisor of a and m. So a is 6, b is 5, m is 10. The greatest common divisor of a and m in this case is the greatest common divisor of 6 and 10, which is 2. And b, which is 5, is not congruent to 0 mod 2. So this has no solution. So this pair of congruences has no solution. So sometimes a pair of congruences has a solution. Sometimes it doesn't. And the Chinese remainder theorem tells us exactly when a pair of congruences has a solution. So the Chinese remainder theorem says the following. We have x congruent to a mod m and x congruent to b mod n. There exists an x that simultaneously solves both of these congruences if and only if a is congruent to b modulo the greatest common divisor of m and n. See, in this case that failed, M and N were 6 and 10, respectively. Their greatest common divisor was 2, but 2 minus 7, that's minus 5, is not divisible by 2. So there was no solution to this pair of congruences. Whereas in the first pair we looked at, again, the greatest common divisor of 6 and 10 is 2. 3 minus 7 is minus 4, and minus 4 is divisible by 2. So this pair of congruences did have a solution. So let's prove the Chinese remainder theorem. So we have, suppose there's a solution, then X congruent to A mod M means X is equal to A plus MU for some integer U, which means A plus MU is congruent to B mod N, or MU is congruent to B minus A mod N. And now this is a linear congruence. This is a congruence in one variable, U, and this is solvable if and only if B minus A is congruent to 0 modulo the greatest common divisor of M and N, which is the same as A congruent to B modulo the greatest common divisor of M and N. So this is a necessary and sufficient condition for a pair of congruences to have a solution. And I can go on from there and we can observe the following. Suppose X is congruent to A mod M and X is congruent to B mod M N. And we have another solution, Y congruent to A mod M and Y congruent to B mod N. So if X is congruent to A and Y is congruent to A, X is congruent to Y mod M. And if X and Y are both congruent to B mod N, X is congruent to B mod N. So this means X minus Y is divisible by M and N. So X minus Y is divisible by the least common multiple of M and N. So X is congruent to Y modulo least common multiple of M and N. And the converse is true. If X is congruent to Y modulo the least common multiple of M and N, then X is congruent to Y mod M. So if X is congruent to A, then Y is congruent to A, and so on. So we get a whole congruence class of solutions. If we go back to our very first example, we had X congruent to 3 mod 6, X congruent to 7 mod 10. The greatest common divisor of 6 and 10 is 2, and 3 is congruent to 7 mod 2, so there's a solution. And the least common multiple of 6 and 10, the smallest integer divisible by both 6 and 10 is 30. So if X is a solution, and if Y is congruent, so Y is a solution, another integer Y is the solution, if and only if Y is congruent to X mod 30. So you have a whole congruence class of solutions of this pair of congruences. And that's the first form of the Chinese remainder theorem. Let's look at a couple more examples. So these are some examples in the book. Suppose x is congruent to 5 mod 21, and x is congruent to 19 mod 56. So the greatest common divisor of 21 and 56, see 21 is 3 times 7, 56 is 8 times 7. The greatest common divisor is 7, and 5 is congruent to 19 mod 7 because the difference is minus 14, which is divisible by 7. So this pair of congruences has a solution. And to find it, again, one way is to say that if x is congruent to 5 mod 21, then x is 5 plus 21u for some integer u. And this has to be congruent to 19 mod 56. If I subtract 5 from both sides, 21u is going to be congruent to 14 mod 56. Each of these numbers is divisible by 7. If I divide by 7, then 3u has to be congruent to 2 mod 8. Let's see. For what number is 3u congruent to 2 mod 8? So u congruent to 6 mod 8. So if u is any number congruent to 6 mod 8, 3 times 6 is 18, minus 2 is 16, is divisible by 8. So I can say u can be any number of the form 6 plus 8 y. So x, which is 5 plus 21u, is 5 plus 21. U is 6 plus 8y. This is 5 plus 126. Let's see, what is 21 times 8 is 168 plus 168y. So this is 131 plus 168y. So for this pair of congruences, the solutions, let me call this V, any number x congruent to 131 mod 168. That gives all the solutions of this set of congruences. Let's check that 131 is a solution. So 131 minus 5 is 126, which is 6 times 21. So 131 is congruent to 5 mod 21. 131 minus 19 is 112. And 112 is 2 times 56. So 131 is congruent to 19 mod 56. So 131 is a solution. If you had to actually find that solution by hand, by trial and error, that would be an unpleasant task. That would take a long time. All right. So that is the Chinese remainder theorem. And I'm going to spend all day Wednesday, I think, talking about the Chinese remainder theorem. And then maybe we'll go on to the last major theorem in this section, which is the Euler-Fermat theorem. Okay. Any questions about that? If not, then we are done for the morning. See you on Wednesday.